Welcome to the first lesson of this course on real analysis. In this lesson, we outline a basic framework for defining and manipulating sets. A set is a well-defined collection of objects. The objects that constitute a set are called the elements of the set. So in this set of animals, the turtle is an element of the set. In specifying a set, we can give an extensional definition, where we list the elements in full, separating the elements by commas and surrounding the list by braces. Here we have a set comprised of the numbers 1, 2, and 3. A set is completely defined by the objects that make it up, so the order and multiplicity of the elements in an extensional definition don't matter. Therefore, the two statements below are true, because all the sets contain the same elements. It is often convenient to assign a name to a set, and we conventionally do so with capital letters, like this. Sometimes it is impractical or impossible to provide an extensional definition for a set. An implicit definition is one where the elements are not listed in full, as the pattern is assumed obvious. This example here is an implicit definition for the first 100 positive integers. The ellipsis is used to stand for the unlisted elements. Implicit definitions should be avoided when possible due to potential ambiguity. For example, it is not clear whether the set below is a set of odd integers greater than 1 or odd prime numbers. The main method of specifying a set is with an intensional definition, using set builder notation, where a defining property is given, called a predicate, that any object either has or doesn't have. In this example, we specify a set we used before with an intensional definition. It is read as A is a set of all x, such that x is an integer which is greater than 0 and less than 4. The vertical bar is read as such that. Even more care is required in defining a set this way, as using natural languages we can run into paradoxes, such as Russell's paradox. There are consistent axiomatic theories on sets, the most well-known being ZF's set theory with the axiom of choice. In this course we do not need this level of rigour, as with enough care it will not be an issue. To say that an object is an element of a set, this symbol is used. For example, the statement on the second line is true and would be read as 5 is an element of the set B, or 5 is a member of the set B. To say that an object is not an element of a set, the same symbol is used with a strike through it. This is read as 3 is not an element of the set B. Sometimes all the elements of one set A are also elements of another set B. We would say then that A is a subset of B. This is denoted by using this symbol, and it is placed between the sets like this. As a real-world example, the set of all halogens is a subset of the set of all chemical elements. A more formal definition of the subset relation would be that A is a subset of B if and only if, for all x, x is an element of A, implies x is an element of B. To express that B is not a subset of A, we would use the same symbol with a strike through it like this. A consequence of this definition is that every set is a subset of itself. In this example, to express that A is a subset of B, but is not the same as B, we would say that A is a proper subset of B, and use the same symbol without the line underneath. A set with only one element is called a singleton set, and is different from the element itself. Here we show the number 7 and the singleton containing 7. Another important set is the set containing no elements, called the empty set, which is denoted with this symbol. Usually, a proper subset of a set X is neither X nor the empty set. We will adopt this convention too. Note as a consequence of the definition that the statement X belongs to the empty set is always false. Given two sets, we can construct other sets using set-wise operations. We will show how to do so first when the two sets are defined extensionally, and then when the two sets are defined intensionally. The union of two sets, A and B, is a set containing all elements that are in either A or B. We denote this using this symbol and placing it between the sets. For example, let A be the set comprised of 1 and 2, and let B be the set comprised of 2 and 3. The union of these is a set comprised of 1, 2, and 3. Next, let O be the set of odd integers, and let P be the set of prime numbers. The predicate of their union is the disjunction of the predicate of O with the predicate of P. You may already be aware that this could be simplified, using the equivalent predicate read as the set of all x, such that x equals 2, or x is an odd integer. The intersection of two sets A and B is a set containing all the elements that are in both A and B. We denote this using this symbol and placing it between the sets. To use the previous example, the intersection of A and B is a singleton containing 2. Next, let E be the set of even integers, and let P be the set of prime numbers. The predicate of their intersection is a conjunction of the predicate of E with the predicate of P. You may already be aware that 2 is the only even prime number, so we can define this set extensionally as a singleton containing 2 as well. As a last example, let J be this singleton, and K be this singleton. Their intersection is the empty set. When the intersection of two sets is the empty set, we call the sets disjoint. The set difference of two sets A and B is a set containing all the elements that are in the first set and not in the second set. We denote this using a backslash and read it as A/B. For example, let A be this set and let B be this set. We would say that A/B is a set comprised of 1 and 2. An aid to memory is to read this mentally as A without B. As another example, let C and D be sets, and let C be a subset of D. We know that every element of C is also an element of D, so C/D is the empty set. For an intentional definition of the set difference of two sets, we would use this predicate, which we would read as A/B is a set of all x, such that x is an element of A and x is not an element of B. That's 3 set-wise operations discussed so far, whose definitions we summarize with intentional definitions on the left and Venn diagrams on the right. They are set intersection, set union, and set difference. To explore the remaining ones, we need to introduce the idea of a universal set. A universal set is a set of all objects under consideration in a discussion. It is usually denoted by either of these symbols, though we will use the one on the right. A consequence of this definition is that in a discussion the following is true for any object X and any set A. The universal set is usually only specified when necessary. Given two sets A and B, where A is a subset of B, then the relative complement of A in B is B/A. In the Venn diagram below, the green area depicts the relative complement of A in B. For example, let X be this set, and let Y be this set, then the relative complement of X in Y is this set. Note that this set contains 2 elements and some authors call such sets doubletons. Given a universal set U, then the absolute complement of a set A is a relative complement of A in U. You will usually see it denoted like this. This operation is just a special case of the relative complement, but is unique in that it is defined for all sets. Note that the absolute complement of the empty set is a universal set. The last type of construction we will consider is a Cartesian product. In order to do this, we need to introduce the notion of a tuple. At this stage, it is best to think of a tuple as a list. Here is a 2-tuple, a 3-tuple, and an n-tuple. The second entry in this tuple is the number 6. We define two sets to be equal when they contain the same elements. In defining tuple equality, we first state that an m-tuple may only be equal to another m-tuple. A pair of m-tuples are equal if and only if the ith entries of both of them are equal. The statements below then are all true. The Cartesian product of two sets A and B is a set of all ordered pairs x, y, such that x is an element of A and y is an element of B. For example, let A be this set and B be this set. Then the Cartesian product of A with B is this set. A and B are called the factors of the Cartesian product. So notice how the elements of A appear first because A is the first factor. As another example, the Cartesian product of this singleton V with this doubleton W is this set. In this last example, note that care must be taken with notation, as the factors of this Cartesian product are actually singleton sets, and so the Cartesian product is comprised of a single two-tuple only. We can generalize this idea by taking the Cartesian product of more than two sets. Observe that in a Cartesian product with n factors, we have a set whose elements are all n tuples. Here is a complete intensional definition of the general Cartesian product. It is read as the set of all n tuples, such that the ith entry belongs to the set A sub I. This concludes the lesson portion of the video. Here is a list of the keywords pertaining to the topics we covered. For the question portion of the video, left-click the number of the question to see the answer in detail. If the media player you are using does not have this feature, you will find the answers video listed as the name of this video with the word answers after it. One effective method is to pursue a question that you may have after every pair of questions. Question 1. Provide an extensional definition for these intentionally defined sets. Part A. The set of all x such that 2x equals 5. Part B. The set of all x such that 3 to the x plus 5 equals 86. Part C. The set of all x such that x plus 4 times x minus 3 times x plus 2 times x plus 5 equals 0. Part D. The set of all x such that the sine of x is equal to 2. Question 2. Which of the following statements are true and why? Part A. The empty set is a subset of any set X. Part B. The set containing the empty set is a singleton set. Part C. The set containing the empty set and the empty set is a doubleton. Question 3. The power set of a set X is a set of all subsets of X and is written as P of X. Part A. Provide an extensional definition of the power set of the set comprised of the letters A, B, and C. Part B. Let little p of x be the set of all proper subsets of x. Then what is the set difference of the power set of x with little p of x? Part C. If A is a subset of B, then B is a superset of A. Create a diagram of the power set of the set comprised of the letters A, B, and C, linking elements that are subsets or supersets of one another. Question 4. Setwise operations practice. Find the union, intersection, set difference in both ways, and Cartesian product in both ways for the given pair of sets. Question 5. An operation, denoted star, is commutative if and only if A star B is equal to B star A for all A and B on which it is defined. As an example, multiplication is commutative. As another example, addition is also commutative. Prove which of the setwise operations are commutative. Question 6. The universal set is often left implicit This means it is unstated as it is thought to be understood. Use your best judgment to estimate what the universal set is for each set and determine the absolute complement of each set. Part A. The set of all x such that x is an even integer. Part B. The set of all x such that 3x squared equals 7. Part C. The set comprised of the letters alpha, beta, and gamma. Question 7. Is it ever possible that the Cartesian product of A with B is equal to A for finite sets? Question 8. An operation star is associative if and only if A star B star C is equal to A star B star C. Determine whether or not set union, set intersection, and the Cartesian product are associative. Question 9. Which of the following is true and why? Part A. A intersected with the union of B with C is equal to the union of A intersected with B and A intersected with C. Part B. A slash the union of B with C is equal to the union of A slash B and A slash C. This question encourages mathematical investigation. Question 10. Investigate a generalized set union and set intersection. Invent your own setwise operation and determine whether or not it is associative or commutative.